Okay, welcome to the next edition of the Petuum Podcast. This is part of our CASL series. So today we'll be talking to Sang, who is the author of Betty, which is a recent addition to the CASL open source framework. Sang, thank you for
Thanks
joining
for
us.
thank you so much for inviting me here. Thank you so much for the introduction, Julie. Yeah.
Well, let's introduce you a little bit better. So where are you right now? You're at your office?
Yeah, I'm in my office in Pittsburgh, Carnegie Mellon University, and I'm a PhD student at Carnegie Mellon University under the guidance of Professor Eric Singh. Yeah.
Oh, wow. Okay. Very nice. So I see how you can connect to Petuum right away.
Yeah, right.
Where are you from? Where'd you grow up?
Yeah, I'm originally from Seoul, South Korea. I lived there until I turned like 25, 6, and then moved to the US for my grad school master's, also at CMU, and then started my PhD in 2020. And now I'm in my third year. Yeah.
Do you like Pittsburgh?
I hated it honestly when I first came here. I mean, like I'm from like Seoul, like a big
Yeah.
city in Korea. So when I first moved here, I thought that the city is a little boring.
Yeah.
But then like since I got a dog, in 2020, my life's been very crazy, and yeah, it's much more enjoyable these days. Yeah.
And what's your dog's name?
My dog's name is Betty, which is my
Uh,
library's name as well.
the plot thickens.
Yeah, yeah,
Okay,
like
so what on the academic side, what first drew you to AI ML?
So for my undergrad, I majored in electrical engineering and mathematics. And at the time, like I was like really into mathematics, but like something more practical than pure mathematics. But like at the time, like if you especially in Korea, that was like very Korean thing. We have like Samsung, and then the semiconductor things are like really big in Korea. But in semiconductor research, people don't use like mathematics that much. So I started like looking for the area that I can use math a lot, but at the same time something more practical. Then I found this, the AI research things in 20 like I guess like 16 when the AlphaGo kind of stuff first came out. And then I thought like this is really cool. And then I started working in AI. Yeah.
Cool. So your career trajectory so far, did you do any research on semiconductors?
No, never. I was never into like the hardware stuff.
Got it. Okay.
Yeah.
So now you're in ML. What's your area of focus with your research?
So I am my primary research interest these days is in auto ML, like auto ML, basically like automating the ML development process so that people without ML expert knowledge can still develop the AI ML products. Yeah. And for that, I also developed my library Betty recently. And now I'm trying to work on building the actual. So like the Betty is more like the backend tool for developing an actual product. And then I am currently trying to, like I said, like I'm trying to build the actual product upon and using Betty for AutoML. Yeah.
On the application layer of
Yeah.
it. Okay, all right. So let's talk about Betty then.
Mm-hmm.
We don't get to meet her. I was excited. I hope you were going to actually bring Betty to our podcast today. But
Unfortunately, she's staying home now. Yeah.
so, what problem are you trying to solve? What's your goal with Betty?
Yeah, that's a really great question. So, about a year ago, I started looking into um like several research topics that I wanted to focus on my, PhD research. Um, and then realized that a lot of really interesting but practical questions share the same mathematical framework, like underlying mathematical framework. And that was something called multi-level optimization. But
Okay.
then so for example, multi-level optimization has a lot of applications like hyperparameter optimization, like new architecture search, adversarial learning, reinforcement learning. But for some reasons, I don't still know why, but for some reasons, all of this, even though all these applications share the same mathematical framework, all of these fields were kind of studied very separately without the shared underlying tool, the unified tool for these applications. So that's why I kind of decided to, to develop a unified tool for all these applications. And I thought that like that is going to have a lot of practical impacts. Yeah.
Yeah, that's really
And right.
so do you think that that kind of fragmentation of AI approaches, I guess we could call it, is that symptomatic of just like academia in general, like people being siloed,
I
or
think
politics of it, or do you think like the
Yeah, I think that's one of the really big trends in especially ML area, AI ML area. So people talk about the same thing using different terms all
yeah
the time. Um, I think like one of the reasons is for the marketing issue. I mean, if you come up with the really cool wordings, you get a lot of fame. And it's good. It's good that like you can draw people's attention from using very fancy terms. But at the same time, I think it kind of really slows down and then make the fields very fragmented, like you said. And as a former mathematics students, I don't like those fragmented,
yeah
things. I like something very unified that can tackle a variety of problems at the same time. So that's why I decided to work on this
I love
problem.
that. That's very
Yeah.
cool. And it sounds like I come from a finance background and I
Hmm.
really hate poor resource allocation. So
Yeah.
having
Right.
a lot of fragmented talent is just terrible resource
Yeah.
allocation. I mean, if there's a way
Right.
kind of unifying that, then
Hmm.
about all the stuff we could get done.
Hmm.
So what is Betty? Like high level, explain it to me like I'm 5. How would you describe Betty?
Yeah, like I said, so the underlying mathematical framework for all these applications is called multilevel optimization. Um, but to be honest, like first of all, I am not very happy with the term multiple optimization because like I say like very little people very few people know about this term multiple optimization even in AI research area. People use multiple different terms like auto ML,
Yeah.
um, like meta learning, hyperparameter optimization kind of stuff for the same mathematical framework. Yeah, that's something that I want to say first. And then so Betty is basically a tool for tackling all these like all kinds of multi optimization problems. But then this multi optimization requires a lot of like mathematical and programming proficiency. So it raises a lot of barriers to normal people to do something with multiple optimization. So and I at the time hypothesized that like that is one of the major reasons why it's not getting popularized, even though it has so much potentials. So my main focus of Betty was basically making this multiple optimization easy, and also scalable, especially reflecting the recent trend of large models, and then unified for all these applications. Yeah, that was like my major goal of Betty, and then that's what Betty is. Yeah.
So let's talk about those 3 things. So the first one was easy.
Mhm.
How do you make it easier than current frameworks that people would use?
That's a good question. So so for the first 2 or 3 months, I guess, when after I started this Betty project, I spent like first 2 or 3 months just for the software application to allow the easy to use programming interface for users. And what I did for that was basically reviewing like other popular deep learning frameworks like PyTorch Lightning or DeepSpeed. And then yeah, I actually learned a lot from those frameworks, and then got inspired a lot, and was able to know like what's the essential part of um, um, the deep learning and what's not essential part of deep learning, and just try to distill the only core part, the only essential part into the library. Yeah, that's like what I did to make this framework more usable and easy to use. Yeah.
So you trimmed the fat off.
Yeah, exactly. Yeah. It was like really interesting because even though this is how I view this thing. So making something easy to use um is very useful. Um but I think one of the problems that I see in academia these days is that people are overly obsessed with publishing papers.
Yes.
Uh, but making something easy doesn't always lead to the publications. They just think, yeah, you did some tedious engineering and then that's it. So but at the same time, like I said, like the multiple optimization requires a lot of like mathematical background knowledge. So it was not very so if you're not like really into the deep learning and mathematics, you're not able to like come up with the framework because it's just it's a lot of mess.
Not, yeah.
Yeah, it's like it was not very straightforward from industry people to work on this like easy to use framework. But for academic people, it was not very incentivizing because it's not going to lead to the publication. But then I thought like there's going to be a lot of potential because personally I am very like practical person. I'm really into practicality, so I want to make a lot of impacts, and I thought that the paper is not the only way to make a practical impact. And I fortunately had some like mathematical capacity to understand all this mathematical concepts behind the multiple optimization. Yeah.
So
So
that sounds very, that I guess touches on another limitation of academia. I personally am someone who dropped out of their PhD program,
mhm,
so I find a lot of limitations to the
mhm,
academic model or academia
mhm,
model, I
mhm,
should say. Um, yeah, and one of them is just kind of that huge gulf between industry and academia. It's
mhm.
almost like they're, optimized for two totally different ends. Like
Right, that's
industry
true.
wants something to be accessible and academia almost wants it to be not accessible because of
Mhm,
it's published. So do you having that kind of approach of, sorry, I'm totally deviating from my script now, I told you I would end
mhm.
up so
Yeah.
having that approach to writing a paper heavily based in mathematics that it is geared towards being accessible to like more of a lay audience, do you find any kind of like pushback from academic peers?
Um,
Or even, and you don't have to talk about this part if you don't want, but
yeah.
I wonder about like getting published and getting into conferences and stuff
Mhm.
if you're trying to make something more accessible. Like, is that accepted by the research community, or is that kind of like frowned upon?
I think so I mean it's always best to do something practical as well as scientific.
Yeah.
But yeah, just like their interests are different. Like industry and then academia's interests are just basically different. Like when I talk to industry people, I think one of the most important aspects for um like products, actual products, is usability. If it's hard to use, if it's even if like your method is going to achieve a really good performance, no one's going to use it because it's so hard to use, and then not many people can use it. Um, but in academia, um, the performance matters. Like that's like one of the most important metric for measuring the superiority of your algorithm or whatever. So I think the trade-off here is basically the performance versus the usability.
Yeah.
For usability, it's probably just better to use the most basic method that achieves the reasonable performance, not the best performance. Um, the basic method, and then build a simple UI UX kind of stuff, the user interface. But to squeeze the performance, you basically have to add like bunch of like random techniques to your models, to your research. But like those the techniques are most of the times not applicable to other tasks than the problem that you're solving. So yeah, so basically there's I think the big trade-off between the usability and then the performance.
Yeah.
Yeah.
Interesting.
So right.
Okay, so you said three things. It was you made it easier, scalable and unified, right? So
Right.
how is Betty more scalable than other frameworks?
So there are several like multiple optimization related library framework,
Yeah.
something like the Higher, Torch Meta, or even Jacksoft recently. There and you can actually write almost like everything you can do with Betty with existing tools like Higher. The issue is that these libraries were released in like 2018, 19, when like meta learning, one of the most popular applications of multiple optimization, got popularized by Chelsea Finn's model agnostic meta learning paper in 2018. And at the time, unfortunately, in 2018, people were not very into large models. So like at the time when they designed the library, they didn't take this like scalability into account. So because of that, these libraries are not able to, and some of the library actually explicitly wrote in their like README file that they are not going to support the this retraining kind
Yeah.
of features, which is essential for large scale applications. But for me, I started the Betty project like only this year, January. And at the time, the large models got already very, very popularized. So I couldn't ignore that aspect. And that's why I took into this scalability issue account when I first came up with the software design for Betty. Yeah, and that's why I think that's one of the reasons why I think so. Like in my personal opinion, I think it's first of all it's much easier to use than other libraries like Higher or Torch Meta. But at the same time, since we consider the scalability issue into account in the design stage, yeah, you can scale this like multi-optimization, meta learning, hyperparameter optimizations to large scale applications than other libraries. Yeah.
So how large? Or actually, maybe I should ask, can you tell our audience a little more about what large models are, what constitutes large models? We've been spending a lot of time on it at Petuum, on like large model operations. But in case anyone hasn't been like blasted with a bunch of GPT-3 advertising or anything,
Yeah.
what's like a transformer model, why is it different than what was happening in 2018 when this other stuff was written?
It's kind of really difficult to provide a definition of the large models because, like, for example, when BERT, which is like
Yeah.
one of the most popular models in NLP, came out in I guess 2018 or 19, it was considered a large model. It has like I guess 100 million parameters in it, and at the time it was considered a really large model. But this day, like GPT has like 175 billion parameter, which is like 10,000 times more than BERT. So it's I sometimes feel guilty to say that BERT still is a large model.
Yeah, because it's not anymore, right? The Sesame Street family where
Yeah, at least it has to be like GPT-2 scale, which is like 1.5 billion or something like that. Um, and yeah, I think with Betty, we for now we should be able to support up to like GPT-2 scale, given the enough computational resources. Yeah. Um, but GPT-3, I'm being honest here. I think it's not able to support like 100 billion parameter models with Betty for now. But if we um think that like that's essential in the future,
Mhm.
we will probably do something about it like later. Yeah.
Can you tell me why? And this is just, would be interesting for me if you can teach me this. Why is it that you couldn't scale to 175 billion parameters? What would be the limiting factor for you other than compute?
So like there, so for scaling large models, like distributed training is like the most important thing. And then um they're like basically three most popular distributed training techniques: data parallel training, model parallel training, and pipeline parallel training. For now, Betty only supports the data parallel training. And in my personal opinion, the data parallel training should be enough for most cases. Uh, but like to train like a more than 10 billion parameter models, you should use some more advanced distributed training techniques like model parallelism or the pipeline parallelism. And yeah, that is for now not supported by Betty, and then that is the limiting factor. Yeah.
That makes sense. Okay, and then the third thing with unified, which I think you touched on a bit, but what exactly is it about Betty that makes it more unifying beyond just like a branding, kind of thing? Like,
Okay. Basically, so I told you that there are other like libraries that do something similar with Betty, like higher research meta. And then those libraries were developed, like I said before, mostly because of this, model agnostic meta learning by Chelsea Pin. And yeah, and I will still say that this like model agnostic meta learning shares the same mathematical framework, underlying mathematical framework. It's just one part of it. It has other like applications like hyperparameter optimization and neural architecture search. But these libraries were motivated by this like model agnostic meta learning paper. So the software design is very tailored for the model agnostic meta learning. So they didn't consider other applications like new architecture search or hyperparameter optimization in general. So in many cases, you have to modify your code a lot to adapt to different applications with those existing libraries. But for Betty, I from the design stage, I thought about this like multiple applications in mind. So that's why I said the Betty is providing a unified program interface for multiple applications. Yeah.
got it. Okay. Oh, I did want to ask you just kind of like the story behind the process for writing Betty, in terms of if you had any collaborators working with you on this, or how kind of like the Betty founding story, even though you.
Yeah, so I closely collaborate with three people for the Betty project. So the first one is Willie Naismith.
Mhm.
I think he's also affiliated with Petuum as some like research director. Um, we had a weekly meeting, and then like he gave a lot of comments and advices on the application part mostly. What we can do with Betty, kind of stuff. And the second collaborator is Peng Tao. I think he was also affiliated with Petuum at some point. He really focuses on this multi optimization in general. With like he's currently a professor at UCSD, and a lot of his students are actually working on gradient based multiple optimization. So I was able to discuss a lot of like practical limitations in doing research in multiple optimization with him, and like some of the like mathematical concepts behind it. Yeah. And then the final collaborator was my advisor, who is like Eric Singh. He's he gave like a lot of high level comments about like what I should picture with Betty, like the having a big picture about multiple optimization with Betty, kind of stuff. Yeah, those three are my major collaborators.
It's like a good team.
Yeah.
Okay, so we have like actually touched on a lot of these technical questions, I think, already. We talked about what multi-level optimization means, but I don't think you just mentioned gradient-based. How can we compare gradient-based MLO to like a more classical standard non-gradient based method of MLO? Like what's the difference and like pros and cons maybe in terms of like applicability?
Okay, yeah, I mean, we talked about some of the applications of multiple optimizations, but I think we've never talked about the concept itself of multiple optimization in general.
Yeah.
And I think that that's kind of really interesting part. So like multiple optimization is basically finding the optimal decision um, that will affect other people. Like so let's say like we are playing a poker game, for example. Your decision, like which card you will use, will affect other players, right?
Right.
And then but basically before you make your final decision, you will think about like how your decision will affect other players' decisions, right? And based on that prediction, you make a final decision, right? Because like those other players' will decision will again affect your situation later, right? So this is like what multi-level optimization is basically. So you think about like how your decisions will affect other people, which will again affect you later. And based on that prediction, you find the optimal decision for you. And if we reframe existing applications like neural architecture search or hyperparameter optimization um, under this framework, so basically, your architecture decision will affect the neural network training. And yeah, and this neural network, after you finish your network training, you have to evaluate your model on the like a validation set or the test set, and you want to find the architecture that maximizes the performance on this like validation or the test set. But the influence is a little indirect because you choose the architecture and then you perform a training for a long time, and then you will get to know how it will perform the validation test set. Um, Same in hyperparameter. You choose the hyperparameter, and then given this hyperparameter, you will perform a training for a long time. And after this long time, you will get to know like how your model will perform given this hyperparameter on the validation or the test set. And multiple optimization is basically the mathematical framework for solving this kind of problems, like this situation. Like your decision will affect other agents, like the model training part, like for a long time. And then after this long time, you will be able to measure the goodness of your decision. And given this scenario, like how to find the ultimate. So this is the basic concept of multi-level optimization. But why, and I guess like your question was, so why gradient-based multi-optimization? Why is it better than other approaches? It's because sometimes your decision can be really high dimensional. Like for example, new architecture search. You can basically come up with like the millions of different architectures, right? Um, it's just arbitrary graphs. Same thing for hyperparameters. You can just tune like one or two hyperparameters, like learning rate or the weight decay values. But actually, you can have like more than hundreds of hyperparameters depending on your setup. And once this hyperparameter becomes really high dimensional, like more than 10, other existing methods like Bayesian optimization fails to scale. It will basically cost you like 100 more times, and then the traditional traditional method. But the gradient based approaches will only cost you like 2 to 4 times more 2 to 4 more times than the traditional, like, non-hyperparameter optimization kind of baseline. So it is like much more cost efficient. And I think this efficiency is really, really important in many practical cases. Yeah, and it's like one of the most appealing example for this high dimensional hyperparameter optimization is what I am calling is like basically a data set optimization. Is it's like in academia, we kind of assume that we are given a clean data sets like ImageNet, and we don't care about the data quality that much. But in real world data science, data are not clean, right? And it costs a lot of you know human efforts and money to clean your data. But what if we can automatically figure out the clean data and then the dirty data and then filter out the dirty data? It's going to save you a lot of time and cost, right? And the basic thing you can do here is basically, so if your sample is clean, you're giving an importance weight of 1. If your data is not clean, you're giving importance weight of 0, right? By doing so, you can kind of filter out the dirty data and then only train your model on clean data, right? But another issue here is that the data sets are oftentimes very large. Let's say, like a million. Then basically you have to figure out this 0 and 1 for these millions of data samples, right? And this like data weight, the importance weight for each data sample can be kind of considered as a hyperparameters. You will only get to know whether your importance weight is correct or not after performing a long training procedure, right? So in this case, like basically, let's say you have like 1 million data points, you have like 1 million hyperparameters, importance weight for each data point. If you're using like Bayesian optimization to solve this problem, like you will never be able to it will take like tens of years, maybe hundreds of years to solve this problem. But with gradient-based optimization, it's only going to cost like 2 or 4 more times than your baseline. And after just putting 2 to 4 more times for this data cleaning mechanism, you'll get the clean data. And so it's going to save a lot of like time and cost for a lot of practitioners, and that's what I think is really interesting application for multiple optimization.
Yeah, that's a very attractive value prop. Costs. Okay, let's talk on the topic of optimizing and costs. Let's talk about infrastructure. And sorry, I have a train that comes by in the afternoons. You can probably like hear it going off back there. But GPUs. So, what GPU memory optimization techniques are you utilizing to support the increasingly larger trend of models? So, basically, on the infra side.
Like I said before, I think we're using like several techniques like the discrete training, especially the data parallelism, and then something called mixed precision training, which is reducing the floating point from like FP32 to FP16 for some specific layers, and like gradient accumulations. And I think this should be good for most use cases. I told you that it's not able to support like GPT-3, but yeah, here is how I view things. GPT-3 can do a lot of cool things, but from the industry perspective, you may be able to make a lot of money using GPT-3. But let's say you make like 100 million using GPT-3, but the large models like GPT-3 cost a lot of money for the deployment. So if you have to spend like $99 million to make a $100 million, I'm not sure if that's the best. That's the better. I mean, this is the better scenario than like making 10 million while costing only 2 million.
Mm.
So I think in the near future, maybe people may figure out like to reduce the deployment cost for those large models. But for now, I think most companies won't be able to afford uh to deploy those large models for their like um products.
Yeah.
And yeah, that's even the case for Bird. Even though the Bird is considered a kind of a small model these days, like deploying Bird on like AWS costs a lot of money. And sometimes it costs more money than like what you make with Bird. So yeah, so that's why I am not like practically targeting for like the larger scale for multiple optimization now.
So then what do you think of OpenAI's business model of just accessing GPT-3 through an API and just doing like those individual calls?
I think it's cool. I think OpenAI's um I think their business model is, I mean, I really, I'm not really in the position to worry about OpenAI's business model, to be honest. But I think they probably did a lot of research when they decide the price for their API. Um,
Yeah, they lowered it recently too. And today they
yeah,
announced their image gen model. They made an API for it too.
right. That's true. DALL-E, I know. Um, Yeah, but I guess a lot of companies, especially like startup companies, are I think the term generative AI is
Yeah.
really big in the VC like
Mhm.
these days. Um, but one thing I've seen like several tweets about this, like you can actually do really cool things with this like generative AI using like GPT-3 or like stable diffusion models. Um, but like um um we only see some cool stuff that are done by this like generative AI, but I don't think a lot of people don't have access to the information on how much it actually costs to do these cool stuffs. Um, and I know like a lot of some companies like recently raised almost like $100 million for their funding with this generative AI. But like I saw one tweet post saying that like what if you raise 100 million and then 97 million AWS?
Yeah.
Yeah,
So, yeah.
yeah,
They're just giving their money to the
yeah.
US at this point.
So yeah, I think we really have to be careful about that. I'm not saying that like they're just burning their money on AWS. I'm not saying that, but that's something we have to be very careful about when using these large models. Yeah.
Makes sense. Okay, so let's go. Actually, let's fit Betty into the CASL framework. So
Mm-hmm.
I know you recently went to Abu Dhabi to a CASL conference, and
Mm-hmm.
we're doing this podcast series specifically with different contributors to
Mm-hmm.
the CASL framework. And at
Mm-hmm.
Petuum, our CTO Trong is also a contributor to CASL.
Mm-hmm.
So, well, you could probably explain this better than I am, but the core of composable, scalable, and automated learning, which we
Mm-hmm.
talked about a bit, how do you see Betty like positioned or contributing to that open source project? Betty is open source, right? I guess I probably
Yeah, but it's an open source. Yeah.
should.
So for now, I am mostly focusing on the automated ML part. So it definitely has a lot of relevance to, especially the automated data cleaning part, just like I
Yeah.
described before, like figuring out the clean data and then the dirty data automatically. So it definitely has a lot of relevance to the A part. And scalable part as well. I just told you that when I started this Betty project, the large models already got popularized. So I had to keep this like scalability in my mind when designing the software. So that's why I added this, discrete training features to Betty. I didn't come up with any like fancy like novel discrete training techniques for Betty, but still it should be able to support a pretty good sized model. And then composable. This is something that I am trying to work on next. Um, so I so as I said before, I'm interested in like automating the ML development process. But then if you think about it, this ML development is not a single stage procedure. It's like a multi stage procedure, like from the data preparations to model training to like deployment. So and there are like a lot of design choices for each of these stages. And then finding the right the design choices is really, really tedious and a lot of efforts. Like we have to basically find the best way to compose different strategies for each stage. And I think that has a lot of like composability issues. And I am hoping to be able to tackle this like composability issues in the future. Yeah.
Nice, cool. Okay, we have a few minutes left. Let's go big picture visions of the future. So just
Mhm.
in terms of Betty, what do you see as the biggest impact that Betty will have on ML and ML systems research and industry in general?
I think first of all, like I think it will make large scale multiple optimization research a lot easier. Um, and one of the core capabilities of human intelligence is basically learning to learn, which is a synonym for meta learning, which has been emphasized by a lot of really famous researchers and industry people, industry leaders like Sam Altman from OpenAI or like Frank Hodder from the University of Freiburg. And I think Betty is the first framework that allows you to, do systematic research for this like meta learning, multiple optimization. So I think that's going to be one of the ways that Betty will affect the academia and industry. But then I have to say that Betty is more like the research, like back-end research tools for developing like various applications. So in that sense, like it's going to be like some of the researchers may use Betty and then develop something really cool. But I'm also one of them. I'm also really interested in like developing applications using Betty. Um, and I am currently developing some like auto ML, like data centric MLOps platform myself using Betty. One of the nice things about having Betty as a backend framework is um, lot of like aspects that we are trying to solve using Betty for this like data centric MLOps platform. Um, but if you have to manually implement each of part, the maintenance cost will be so expensive. Like every time you have to update each part like separately. But if all these small parts share the same backend, um, once I upgrade the Betty, once I update Betty, every parts get updated as well. If Betty becomes more efficient, then those parts also get more efficient. So I think that's like one of the very exciting part of Betty. Yeah.
Yeah, cool. Application layer, very exciting. So so platform product. Are you thinking of any other applications?
Um. Yeah. So I talked about like the data, like filtering the clean data, dirty data, filtering out parts, but actually it's a lot more complicated than that. There can be actually multiple different ways to clean your data. First one is, giving like importance weights to each data sample, like 0 or 1. But you can also like you can also correct the wrong data into a clean data. That's also another option. And then the wrong parts about the data can be in the both input space and then the label space. And then yeah, in this case, you have to have like different algorithms for the input space and then the output space. All these like kind of data cleaning mechanisms can be formulated as like AutoML multiple optimization problems, and then I am developing applications for each of these cases. And I'd like to combine all these things to build a data-centric MLOps platform.
Very cool.
Future, yeah.
Exciting. Very exciting. Okay, so let's go even bigger picture then. What are you most excited about in the field of AI right now?
I think even though like we've noticed a lot of advancements in AI, I think we are still in the really early stage. If I have to make a comparison, I think it's like a compare in like 19 like 60s, 70s, like before the personal computer era. Only it's available to very specific group of people like AI experts. But I think we are getting closer and closer to a democratization of AI. In the next like 5 to 10 years, I think more people should be able to use AI without having like this like high level education. Yeah. And I think that's like the really exciting part. And that's what I'm working on as well.
Yeah, very nice. Is there anything about the current and future field of AI that has you worried?
That's a great question. That's a very interesting question. Again, I don't think this is like AI particular problem, but it's about the um efficiency of the AI research in general. I think a lot of people are doing AI research for like their own fame kind of stuff.
Yeah.
Yeah. And that doesn't sometimes really benefit other people. And those people are really smart. I mean, those people are like actually really smart. And then I feel a little sad that like people are doing. I mean, they can use their talents for something more practical and something more meaningful, impactful. Yeah, that's like my basically. It's probably because I'm in academia. That's like my biggest.
Yeah, that sounds like
Concern.
another symptom of academia.
Yeah.
So where do you see the industry trending in the next like 5 to 10 years?
First thing is that democratization of AI. The more and more people will be able to use AI without the proper like a higher education. But at the same time, I think the large models will change the world in many ways. But to be honest, I am not an expert in the large models. So I can't tell how it will change the world, to be honest. But I have a feeling that it's going to open up a lot of new opportunities in general. Yeah.
Cool. Okay, so what's next for you? When do you finish your PhD?
That's a good question. So I'm not sure when I will be able to finish my PhD, to be honest.
Yeah.
But I am personally very interested in starting my own startup companies. Yeah. Yeah, I talked about this like data-centric ML platform, and I think um, that is going to be the main focus of the company, my startup. So in the next year or two, I will probably mostly spend my time on this project, and um, yeah, that's my plan.
That's
And
cool. That's very exciting.
yeah,
Well, welcome to industry.
thank you.
Yeah. Well, it was very nice talking to you today.
Mhm.
Thank you so much for sitting down with us.
Thank
Um,
you so much for the invitation again. Yeah.
yeah, this was great. We'll keep in touch and
Mhm.
let us know what the future holds for Song and Betty.
Thank you. Right.